So good evening everyone, welcome to the 9th lecture. So actually we have 50 students in the class, so some of you probably are not attending. I mean the ones who are not attending, which is okay, I guess. Okay, so let me start with announcements as usual. Use the discussion board for any questions you have, for example for graphical models. Since it was not covered in the first assignment, it's going to be a huge part of the second assignment if you have seen it. So use the discussion board for any questions you have. There's a feedback form for each lecture in case you didn't notice till now. So this is the 9th lecture, so there are 9 feedback forms, so you can use them. Assignment 1 grades are out, and project grades are also out. I will check. So mostly it's been graded by the TA, but I'll also check. And if you have questions, please address it to the TA or on me. Okay. Assignment 2 is due at the end of this month, which is very close, given that there's a spring break in between. And the in-class exam is on April 5th, which is also quite close. It will cover graphical models and the first part, some of the deep learning topics that we discussed. And remind me to break at 90 minutes because somebody gave me a feedback that I went over by a few minutes last time. Okay. So today we're gonna try to finish. Yeah. For the exam. Okay, so actually not exactly a sample paper, but we have dedicated one full session, right? So exam review will hopefully cover the questions which will be similar to the exam questions, right? Yeah, so today we're gonna cover the third major piece of the graphical models puzzle, and also try to finally kind of touch base on the key more applied topics that you might have seen scattered through the literature. So today you'll actually come full circle and try to appreciate why we studied conditional independence and graphs in the first lecture, and then studied inference in the second lecture. Okay. And then we're going to look at reinforcement learning or online learning problems. Okay, so before I start with the review, there is a UIC Student Research Forum event, which is on April 3rd. It basically students showcase their research, but it can also be promising class projects. So in case you're interested, you are highly encouraged to participate, especially because this is an advanced prediction models class, as in it's an elective and it's also for master students. So with the 3 people effort, you can actually get brownie points by showcasing the same thing at this event. Okay. So any questions about the first assignment, the first project, or anything else in terms of logistics? Yeah.
Would it be possible to set up a separate lab time where the TA can go over the solutions for the assignment 1? I know it's very open-ended, but in other courses it's been very beneficial to have a separate lab where we can break down exactly what's the optimal way of resolving the problem.
Yeah. So you're saying not in the office hours?
Not in the office hours.
Okay.
As in,
lab session for the whole class?
Or just available, and if let's say 25-40% of the students are able to attend at a certain time, I think would be beneficial.
Okay, scheduling another meeting time after, in addition to what we have scheduled is going to be tough. But I highly encourage you to come to the office hours because, I mean, if it's very beneficial to you because most of the other students will not come, so you will have one-to-one, more tailored training, right? We can try to see if we can arrange a lab session for assignment 1, but I cannot make promises because finding a common slot for where everybody agrees that this is a fair time slot for them is hard once the semester has started. If the office hours are not convenient to you and it's been already 9 lectures or whatever, 9 weeks, then send me an email and we'll try to make some alternate arrangements. But do show up and meet the TA or the instructor if you really want additional feedback because it's free. At least office hours are definitely free. Try to take advantage of them, right? Is that somewhat satisfactory? We'll try to see if we can get a additional session, but it's probably hard.
Would you be opposed to me posting a Google questionnaire as far as student availability in the discussion board? And if the majority of students can meet on a certain day, maybe
yeah. But some students will now raise a question that it's unfair to them, right?
Yes.
That it's going to be
majority rule.
No, this is we are using absolute majority here. So even to change the dates, we had to get everybody's input. So yeah, why don't you try the office hours first, or maybe set up an appointment and then we can go from there.
Okay.
Maybe in the next week. Let's see if it addresses the questions you may have. So, any other logistical questions? Okay, we spent 10 minutes on this. Okay, let's go to the review, and then today we're gonna finish up the last piece of inference, which was sampling. It's actually a very interesting and very useful technique to learn, and it's independent of the graphical models that we are studying today. So you can use sampling for a lot of other problems that you may come across. Next, we're going to look at learning. So learning has actually quite a few sub-problems put together into one topic. So you can do learning with a directed graph, with an undirected graph. You can estimate the parameters, which means the factors, the parameters that dictate the factors. For example, if there are conditional probabilities in the directed graph, or just the factor terms in the undirected graph, how do you estimate the parameters for those terms? You can also estimate a graph itself. You can figure out whether a graph of a graph needs to have a certain edge or not from data. And there's also issue of complete or incomplete data, where some data may be missing. It could be question marks, or you may never observe certain random variables. Okay. And in applications, we'll try to see, given time, we'll try to see hidden Markov models, which are very useful for time series analysis. We'll look at latent Dirichlet allocation, which is interesting popular method for topic modeling. We'll also look at a particular clustering technique called Gaussian mixture model, and we'll also, if time permits, look at conditional random fields, which are also used for example, text processing and so on. Okay, so review again. This is a quick slide saying why we are looking at graphical models. When you don't have structured data, or even when you have unstructured data, if you want to impose domain knowledge, then you can use graphical models. So if we have seen use of CNNs for image processing, right? So we can actually use graphical models for certain image processing tasks like image segmentation or image denoising. Okay, so we can use graphical models for both structured and unstructured data. But the way we have looked at graphical models, we have defined random variables. So you can imagine them to be ideally numbers. So for example, pixels are also numbers, but you can think of these as numbers which represent, for example, the outcome of a random event, like the weather, the stock market price, or something like that. So last time we looked at, we spent some time on undirected probabilistic graphical models. So here you have the random variables, and the undirected probabilistic graphical model is defined as a product of something called potentials over cliques of graph G. So for example, in this graph, for example, one set of cliques are AB, BC, and AC. So you can define what are called potentials. Potentials are just functions. So in this case, since each clique is has two variables in its scope, in the sense it's just a function with 2 arguments, you can just completely enumerate the function, assuming that if the arguments only take binary values, then you can completely define what the function is using 4 numbers. Okay, you can define these 3 potential functions or potentials, and then the product of these potentials gives you the probability of a particular configuration or a realization. So probability of capital A equal to A, capital B equal to small b, and capital C is equal to small c is the product of these numbers. Of course, their product, since these functions can have arbitrary values, you need to rescale this definition of the probability such that it sums up to 1 over all configurations, and that's what we are doing here. So this is just a normalization constant. In this case, it's some number. And we also said for undirected graphical models, from the graph itself, we can easily read off conditional independence properties, right? So there were 2 versions of this. The global Markov property, and that's where they are also called Markov networks, is because you can kind of partition the graph into, let's say, 3 sets of nodes, and 2 sets of nodes are, let's say, A and B are conditionally independent given a third set C, if all the nodes in A and B are connected through nodes in C. Okay, so every path connecting a pair of nodes where the first node is in A and the second node is in B, that passes through C. So given C, then those 2 parts are conditionally independent, and that's globally for any, if you partition the graph into any 3 parts, then this is true. If this holds, then they're conditionally independent. You can locally also try to understand what's the conditional independence property of a single variable. So you can focus on one variable and then look at its neighbors. Then given its neighbors, that random variable is conditionally independent of everybody else in the graph. So that's the local property. So reading of conditional independence in undirected graphs was easy compared to, let's say, some nuances were needed for the directed graph models. Then we looked at what is called the factor graph. These graphs are just additional annotations, for example, which also capture the factorization in the graph itself. So if you look at this graph, you can't figure out which cliques were used in the factorization, in the representation for the joint distribution, right? For example, here, by just looking at the graph, you don't know whether there were 3 potential used or a single potential, because ABC is also a single clique. So a single function was used or not. So to address that situation, factor graphs were defined. So where factor graphs is, for example, if you have a potential for every 2 clique, then you would insert a square node on every edge, and then you would have these many factors. So 6 factors here. If you had a single factor, because this is actually a clique, because every vertex in this graph is connected to every other vertex in that graph or subgraph. So since it's a clique, you can define a single factor. Okay. So there are 2 factor graphs, 2 different factor graphs, and from these you can just read off what the factorization is. Any questions at this point from last lecture? Okay. So the inference objectives that we tried to address last time were basically what are the types of problems that we look at. The problems are finding the mode, which is that configuration or that assignment to the random variables, which maximizes the probability, right? And for example, you can also compute functions of random variables like the expectation, because expectation is a function of the function over whose expectation you want to take, and also the joint distribution. Max marginal is just an example inference problem where you're trying to find that xi which maximizes the marginal, where the marginal is taken by summing over all the other random variables. Okay. And a conditional probability is just the probability of a random variable given all the realizations of the other random variables. To compute these, having the graphs helps, and to kind of motivate that, we first looked at a very simple algorithm called variable elimination. Then we touched a slightly more advanced algorithm called belief propagation. And today we're going to kind of finish up on the third set of algorithms, which are approximate algorithms. They don't solve these inference problems exactly, and these are called Markov Chain Monte Carlo methods. Okay. So variable elimination was quite easy to see, but for example, but it's hard to kind of order the summations that you want to do. So what is exactly variable elimination? So let's say we have this graph. So it has 4 random variables and 4 factors. Okay. So you can read that these are the factors from this graph itself. And let's say we want to find the marginal probability of a comma b. So it's as good as saying you can put this in one big node and say there's a big node, e here, and then you just want to get rid of the other random variables, right? So you want to sum over both c and d. So let's say you pick variable ordering, let's say d. Then you can push that summation inside because of these factors and compute this for all c and and define that as a function, which is a function of c. Okay, so when you do this, you're actually eliminating the variables, and that's why it's called variable elimination. Why did we choose d? That's arbitrary choice. If we had chosen, let's say, c, maybe we would have gotten some other function, which would be new c to d of d, right? And then we could still proceed, right? So there is 2 choices here. First marginalize or first sum over d's to get intermediate function, which is this, and then sum over c, right, which is shown here. So this is just substituted here, and then the next step would be to sum over c. We could have done it the other way around, and it's not clear how to choose one or the other, and so that's where we kind of stopped with variable elimination and started looking at a more general version of variable elimination called belief propagation. So belief propagation kind of expands on the idea of these renaming of functions that we saw, or pushing these summations inside where they actually matter, and define the notion of messages and message passing. So consider a branching graph. A branching graph is nothing but a factor graph which doesn't have cycles. Okay. So just looking at this graph, you can see that there are 5 factors. Let's say which are these. And again, let's say you want to find probability of a comma b. Then last time we went through this example where we define these messages, which are essentially similar to what we defined in the variable elimination example, which are these functions which are passed from one node to the other. So we have five nodes which are variable nodes, and we have 5 factor nodes. So all these are nodes. Okay, all these nodes pass messages to everybody in their neighbor, everybody who's their neighbor. In this case, I'm only showing, for example, let's say F2 is getting messages from some of its neighbors and sending message to one other neighbor. It actually has to do the same thing with C, with D as well. So in the sense, it will get a message from B and D and send a message to C. And the other case is it will get a message from B and C and send it to D. So that's the notion of message passing from a system point of view, right? Every node, whether it's a variable node or a factor node, will send messages. Okay, and the protocol is it's gonna get information from, let's say a particular node wants to send a message to some target node, one of its neighbor. Then it's gonna collect messages from its neighbors, who it's excluding the target, and do some local computation and then forward a message. Okay, that's a local version, and that's actually the is the key template for belief propagation. So belief propagation has 3 ingredients. One is initialization, which is to start the algorithm, and there are 2 variants of how you pass messages, because there are 2 different types of nodes here. One is a variable node and one is a factor node, and so that's why the local computations are kind of differentiated. So initialization is quite straightforward. Let's say there is a single factor which is only connected to a single variable. Then the only message that it passes is just the f of x. F of x is the factor, if you remember, from the factorization of the joint distribution. Right? So it will just pass its message to x is just going to be f of x, that factor in that joint distribution or the factor representation. And the message from an extremal leaf, in the sense that if a variable node is only connected to a single factor, then the first message or the message that it passes to its only neighbor is just going to be 1. So for all x, f of nu of x is just equal to 1. Okay, that's the message. So that's the initialization for the ends of the graphs. So once we have taken care of the ends of the graph, what are the messages which any node in between, which has more than one neighbor, will pass around? and that was illustrated by this diagram where first we look at the message being passed from a variable node to a factor node. In this diagram, we have 4 factor nodes which are neighbors of a variable node. So first thing, it should be very quickly to check is that a variable node will never have another variable node as its neighbor. Okay, that's just the way we define factor graphs. Okay, so this node has 4 factors as its neighbors. Let's say it wants to pick one of the factors, let's say factor f, the node corresponding to factor f, as the target node where it wants to send a message. Okay. Now it's going to look at its other neighbors, let's say 3 other factors, f1, f2, and f3, and these 3 factors must send some message to it, okay, to this node. So let's say they sent these 3 messages. Okay. So what should the variable node do to create a new message? So it's a recursive step. So it'll try to take these messages, and in fact it will just take the product of these messages which were given by the other factors and just pass that product back to the target factor. Okay, it can do, now you can see I only focused on one factor node, so you can replace f here and f3 there, and you can do the similar operation. Okay, and the message from a factor variable to a node variable, a factor variable to a factor node to a variable node is very similar to the previous step, except it's going to get these messages, take the product just as before, but the special thing about the factor node is that it has its own factor term, right? The factor, which you remember from the factorization expression of the joint distribution, that term is also there. And that term, since it's a factor, it's a function of, in this case, in this example, it's a function of 4 random variables, right? So that factor will be a function of 4 random variables. So you need to sum over all the random variables which are not relevant to the target. Okay, so that's what this summation is doing here. So you multiply all the messages, multiply that intermediate term to the factor that this node has, and you sum over all the variables that are irrelevant to the target node, right? There's only, all these 3 variables are summed over here. That's all that representation means. And so that's the message from a factor to a variable node. Any questions here? We have gone through an example last time, but now I'm just mentioning the template of how the algorithm would look like. In your assignment, you have one of the questions is asking you to write this algorithm for a small factor graph. So in fact, I think it's the same factor graph that we are studying here. So and you'll also have to use a particular package called NetworkX, which is a nice Python library for representing graphs. So you can just easily create a graph in NetworkX and then write a code to do this message passing. Okay. So a second variation of belief propagation. So the previous the previous algorithm actually computes marginal. So once you do pass these messages, you can actually compute the probability of x. So you can get rid of all these other variables in the actual graph. It's not in this graph, but let's say there was a huge graph where you cared about finding the probability of x. Then that summation that you would have done naively, by doing this, you can compute that very efficiently. Okay, if we just plot computation time required. It's true for only tree structured factor graphs. For factor graphs which are not tree structured, there are heuristics or approximate methods, and we have not gone into those details. Okay. Now, if you want to compute the maximal state, what is the maximal state? It's just the x star, which maximizes, which is that configuration or that sequence, that set of realizations of the random variables that maximizes the joint distribution. Okay. Now this computation is also, if you naively try to do it, it's like enumerate and figure out which number is the maximum. That's a bad idea. And belief propagation, one version of belief propagation called the max product belief propagation algorithm solves this problem. Okay, and it has the same 3 ingredients, very similar to before. In fact, the initialization and the variable to factor messages are the same. The factor to variable messages are slightly different, which is that previously you had a summation over all y's which are not relevant, which are in the scope of the factor but not the target variable to which you are trying to send a message. So the message changes from a sum to a max operation. So that's why it's called a max product algorithm. Okay. In addition, you actually need to track the values achieving the maximums as well. So you need to have kind of a store to remember that which y star or which bunch of numbers, for example, in this case, y1 star, y2 star, y3 star have to be remembered. Okay. So this is what we saw last time. Any questions? How many of you are completely lost with respect to belief propagation? It's a very interesting algorithm and kind of stretches your mind in terms of dealing with joint distributions, and dealing with joint distributions gives you a very good grasp on any problem that you want to work on, whether it's classification, regression, or any other data density estimation, clustering, and so on. So we'll see a few examples towards the last part of this class, where hopefully you can remember that, yeah, okay, this technique is a special case of what we have studied so far. So let's go to the next topic. So in inference, we said we looked at variable elimination and we looked at belief propagation. We're going to look at one additional set of methods called Markov Chain Monte Carlo methods, and these will be useful in doing approximate inference. So what do you mean by that? So BP and variable elimination compute exact probability of exact marginal probability, or the exact max marginal, for example. Now, but the limitation is they only work for the exact computations are valid for a tree structure factor graph where there are no cycles in the factor graph, right? If you remember, we had cast both directed probabilistic graphical models and undirected probabilistic graphical models as factor graphs. We can work with both as factor graphs, and that's why we had a unified inference bunch of methods, right? Now we will try to use numerical sampling because it's a joint distribution, and we want to infer, let's say, the marginal or functions of this joint distribution. We'll resort to sampling from this joint distribution somehow. Directly sampling from the joint distribution is going to be hard, as we'll see, and so that's why we are resorting to some clever sampling techniques, and that's where we get to Markov Chain Monte Carlo. So what is the Monte Carlo part? It's just very straightforward. It's just if you want to, let's say, find a function of your joint distribution. This is a function of your joint distribution. Do you agree with that? Expectation operation, or the expectation function, is a function of your joint distribution, right? That's because expectation of f is depends on the joint distribution, right? So the Monte Carlo part is saying, okay, you want to compute the summation. Let's say you have 100 random variables. They are binary value. That means the script x will have 2 to the power 100 potential realizations of these random variables, right? Do you agree? Okay, so instead of doing a sum or 2 to the power 100 such terms, right? What they suggest is, okay, you just collect some L samples. If you could draw samples from this distribution P of x, okay, let's say L is 100,000 or something like that, which is much lesser than 2 to the power 100. Then we just take the summation, evaluate the function at those 100,000 samples, and call it f hat, and then call this the actual evaluation of expectation of f. Okay, you wanted to evaluate expectation of f, you got f hat. You're happy with that, in the sense that it's actually a consistent estimator. In a sense, expectation of f hat with respect to b is actually expectation of f. There are some other nice properties, but what I'm saying is this is the approximation, and it crucially relies on drawing L independent samples. Okay, and now rest of this topic is all about how do we sample, right? And why are we thinking about how do we sample? Because sampling from that huge factorization is not trivial. And in fact, this whole sampling business, from sampling from a highly complex joint distribution, is not specific to graphical models. There could be other factorization. There may not be a factorization, and still you may want to sample from the joint distribution. And last time we looked at a couple of these generic techniques called rejection sampling and importance sampling. which are just generic for any joint distribution. If you're not able to sample from something, then you create something called proposal distribution. In rejected sampling, that proposal distribution somehow covers or overshadows the original distribution that you wanted to sample from, and somehow you are able to create samples from the original distribution. Similar thing is done in importance sampling, where you again have a proposal distribution. But let's not go into the detail of those two techniques because those are generic. We'll try to today focus on Markov chain Monte Carlo techniques. So these are just Monte Carlo techniques. There is no, in every step, you're generating a sample that has nothing to do with the previous sample that you generated. Okay. Here, we're going to generate samples, but they are somehow going to be dependent on what you generated the previous time. So they are not actually independent samples. Okay. And that's why there's this notion of Markov chain. We're going to look at two methods, Gibbs sampling and Metropolis Hastings sampling. Any questions about the route that we're going to take? Is this clear what we're trying to accomplish? Okay. So Gibbs sampling version of the problem is as follows. Let's say we want to look at this graph, this directed probabilistic graphical model. It has 6 variables, right? And let's say we want to sample. Okay, let's say we want to sample. We want to generate samples from this graph. Okay. Now the idea of Gibbs sampling is this intuitive idea where, okay, first of all, notice in terms of notation, notice that the random variable subscript represents the random variable, okay, or the realization of the random variable. The superscripts represent the sample index. Okay, first sample would be a vector of 6 coordinates, which would be 6 numbers. Okay, for example, if these are binary numbers, if these are binary random variables, then it will be x superscript 0 would be some realization like 101001, something like that, 6 dimensional. Now the idea is to sample the sequence by going one level below, in the sense we'll update one variable at a time, in the sense as follows. Let's say I have x0, some sample I already have. I want to get another sample x1. The way I'm going to get x1 is I'll start with x0 and then I'll try to sample just x subscript 1 for the first iteration. Okay. And then given x0 and one coordinate, I'll sample another coordinate x2 and so on. I mean, I'm not telling you which sequence you're supposed to sample because that's just arbitrary, but you sample one coordinate at a time, which is what this update by one variable means. But you notice that if I want to get a sample of x4, at least in a directed probabilistic graphical model, if you have samples for these other random variables, which form what is called the Markov blanket, or basically in terms of d-separation, think of this as if this is set C, then x4 is conditionally independent of x1 and x2. Okay, so if you had to sample x4, given let's say x4 was the last guy you are trying to sample, then probability of x4 given the previous 5 coordinates that you sampled is just the probability of x4 given 3 coordinates that you need to sample, and these 3 coordinates are just the neighbors, roughly the neighbors of this random variable. Any question? Any confusion? So all I'm saying is, if you have x0, I'm going to first get x1. Let's say I go x1, x2, x3, x5, x6, and x4. So I'll get x1, 1, which is going to be a realization, which is what? Probability of x1 given something. In this case, it's going to be all the values of x0. I'll write this later. Then you'll get x2. So the superscript represents the sample index. So after 1, 2, 3, 4, 5, 6 such operations, you'll get x1. Okay, this is a 6-dimensional vector. This is a 6-dimensional vector. To get from here to here, I'm going to go sequentially and sample one variable at a time. And this is that. Let's say I try to sample the first variable, the first coordinate. I'll get it from some conditional distribution. And similarly, second coordinate from some conditional distribution. Let's say in this example, we just had that I'm sampling x1 4 last, and that's why I'm saying it's a probability of x4 given everybody else, but given everybody else is not needed because given some subset of it, it's independent of these other guys. Okay, it's conditional independence property. So what is this everybody else? It's x3, x5, x6. So in this case, let's say you sample. So given these values, it's independent of these other guys, which are x1 and x2. Let's say, so by the time you reach to x4, let's say it's the last guy in this iteration, in this to getting to the next sample, then you have already sampled these 5 guys. So you can condition on these guys, you want to get the 4th coordinate. But what we're saying is you don't need the 2 of them because they're conditionally, these 2 are conditionally independent of x4 given the intermediate guys. Okay. That's the conditional independence property from the first lecture on this topic. So let's look at another example, and this is more simpler. So let's say we want to sample from, so this is a, first of all, this is a directed graph, right? Directed graphical model. In this case, I think it's something related to medical diagnosis, where there's a couple of random variables. There's okay. There are all these random variables, and let's say we want to sample a new value from W. Okay, W is this cold weather random variable. Okay. Now, how do you sample from W? Right? Yeah. How do you sample from W given all these other random variables? You can firstly notice from 2 lectures ago that condition on flu and cold, this is independent of everybody else, right? So probability of W equal to W given, let's say, some bunch of realization of all the other random variables is just a function of the 2 random variables that it's a parent of. Okay, this is a tail-to-tail relationship. Okay. And it's also called a Markov blanket, but you can think of it this way, right? Condition on these guys, everything else is gone, so that's why it's called a Markov blanket. And so to get a value for W, we actually just need to focus on this. Let's say the realization of this random variable is 1, and the realization of this random variable is 0. Let's say, okay. Then what do you do? So now we have reduced the huge, bigger graph to a smaller graph, right? We only care about these 3 guys. Why do we care about these 3 guys? Because this was what we got from last slide, that we got rid of all the other random variables, right? We just left with flu and cold. Now, probability of W given flu is equal to 1 and cold is equal to 0 is just proportional to, you can just use Bayes' rule to get this probability to be equal to the probability of F given W times, the joint probability of these divided by the probability of F and C, and the joint probability is just the product of the 3 terms here. Is this step clear from this to this? Okay. Okay. If it's clear that we can go from this conditional distribution to some numbers that we can get from the product of these guys, then we can look at our probability. Then we care only about these 3 factors, or these 3 conditional distributions, or basically those 3 tables, right? Which are just listed here. And let's say these are the numbers in those tables. So we are doing inference, right? So we already have these numbers. So then we can look at what's the value for W equal to 0 given F is equal to 1, and what is the value of W equal to 0 given C is equal to 1, right? So we are now looking at the condition where W equal to 0. Let's say W is just binary, right? W is binary. So probability of F is equal to 1 given W is equal to W is you can read it from here, right? And probability of C is equal to 0 given W is equal to W is, you can read it from here. Sorry, this has to be C. And probability of W equal to 0, you can read it off from here. Okay, and so that's this number. And similarly, you can read it off from the other state as well when W is equal to 1, right? Are these two steps clear? How I'm reading off this product basically for every value of W. That's what I'm doing, right? Why am I doing that will be clear in 2 seconds. So probability of W equal to W, the original probability that we wanted to find out, right? Probability of W equal to W given these two things, which are called observations, evidence, or whatever, conditioned random variables. You're going to actually have to rescale them. These are numbers which are not going to sum to 1, right? W can only take 2 values, so if this has to be probability, then it has to sum to 1. It doesn't, so that's why there's a proportionality sign, and we divide by the sum, okay? And that sum just happens to be this. Now, given probability of, so you have this conditional distribution, follows this, has this probabilities, then you can just sample a new W, right? This is coin flipping, so you'll assume that you can at least do coin flipping. So what's the difference between what we did now and when we saw the graph and we wanted to sample from W, right? You can't just sample, yeah, number of variables has changed, but what I'm saying is you can't just sample from here and say that that's the realization of W, right? When I've given you some evidence, you really have to go through this procedure to get different samples of W, right? Given the evidence, the probability of W equal to 0 and the probability of W equal to 1 has changed. So how do you compute that, and how do you get new samples? That's what we're showing. So here, since it's a single random variable, there's no really the Gibbs sampling procedure happening. Okay, it's just x0 to, in fact, there is no x0 to x1 happening here. It's just how to sample a marginal, in this case one random variable, given some evidence, which is these two. That's all is being shown in this example. So we are not really doing this yet. We'll get to that in 2 slides. Okay. So let's say we wanted to, let's change the objective. Let's say we wanted to sample some realizations of cold, right? So this is a graph in which this random variable is related to other guys. Now you want to get some samples for cold. Again, cold is a binary random variable, and you want to get some samples from there so that you can compute the expected cold value or something like that, right? Now, how do you compute that? First, you need to notice that cold is actually is independent of pollen and, let's say, itchy eyes and fever, given all these other random variables. Okay. You can verify that actually in the sense of, if I actually told you this assertion that cold is independent of pollen, itchy eyes, and fever given these random variables, you can check the deseparation condition, right? Which said, let this be C set, this is be A, and let this 3 be B, and you can actually check from deseparation that is true. But a more straightforward way is, given a graph, you can convert this graph into an undirected graphical model. I think we touched upon this in the previous lecture. Okay, how are you going to do that? You actually, for every node, you're supposed to, if you have 2 parents which don't have an edge between them, you create an edge. Okay. And once you create an undirected graph, then you can just look at local Markov property. So if this node will have an edge to this, and this it'll also have an edge to flu, and it'll have an edge to cold weather if you do that operation. And so given these variables, it's independent of, conditioned on those variables, it's independent of all these other guys. Okay. And that's called a Markov blanket. It's just yet another name for the same thing. Is that clear? If it's not clear, then you do the deseparation thing, and you will see that this is independent of three additional random variables. So that's good. So you repeat the same thing as before. So you are only dependent on 5 random variables instead of this additional random variables, right? And if you are dependent on 5 random variables, then you can actually, and you have been given realizations of those 5 random variables, let's say, in some step you have been given realizations of other random variables, right? If you have been given those realization of 5 random variables, it's actually just the product. You can just read off probability of C is equal to C by taking the product of the terms involved. So what are the terms? So this you can actually just rewrite it as a joint distribution using Bayes' rule. So probability of C, comma W, comma F, comma S, comma H, comma A. Okay. And if you just look at all the terms in your joint distribution factorization that have these variables, that will be only these terms. Okay. And since all these other guys have been given, you can just read off what are these probabilities, right? For example, probability of W is equal to 1. You can just read off from that that table that we saw, which had just two numbers, 0.4, 0.6, for example. Probability of F is equal to, let's say, 1, given W is equal to 1. Again, you can just read off from that conditional probability table. So, I mean, this assumes that you've been given everything else, and so you can find the probability of C is equal to C as just the product. You don't even have to. I mean, you'll get this some number, and similarly, if C has another realization, okay, let's say C is binary random variable, then C is equal to 0 and C is equal to 1, you'll get two numbers from which you can, again, it's a coin flip with that bias, you can flip and get a value of C. Okay. Is that clear?
And how do we relate this to this?
Relate what? This time?
So like we are moving from x0 to x1.
Yeah, so if you look at the intermediate stage, it's something like this, right? Probability of a random variable given everything else. So actually, yeah. So here, let's say the first step, you're actually saying x1 given x0 is equal to x00, x1 is the example, right? x2 is equal to x02, all the way to x6 is equal to x60. Okay. You're basically just keeping one of them.
And check for each possible state.
No, you just, so the way it works is, so you have a realization, 6-dimensional vector, right? So those are these real, out of 6 you're taking 5 of them, okay? And given the 5 of them, you want to find the probability of x1, that's its binary. Once you find the probability of x1 is equal to, let's say, 1, x1 is equal to 0, then you can sample x11.
And these 5 variables in all will take 32 different combinations.
No, I mean x0 is fixed, right? It's a specific realization, so it's some 6 numbers, 6 coordinates. So let's say x0, in this case, let's say it's all binary, so let's say x0 is 0, 1, 0, 1, 1, 0, something like this. Then these are all fixed. Okay. So conditioned on them, you want to find probability of x1. That's why we're looking at condition. And actually, it's the same. So there's going to be 5 conditioned random variables in every step. I mean, the first step you're using previous guy, but in the next step you can use x11 as one of the conditioning things when you're doing x2. Any questions here? Or in general, I mean, I've written it as when you don't have evidence. But basically, what I'm trying to say is that when you try to, so we are in Gibbs sampling, an intermediate procedure is to sample one variable at a time, right? If you have n-dimensional, if you have n random variables in your graph, then you have to take n micro steps, right? When you're doing that, you should only care about, if it's a directed probabilistic graphical model, you should only care about factors which involve xi and some other and factors which are children, which belong to the children of I. Okay, so you can see that here, right? So code and factors which are children of this guy. So SOR and H, S and H. Okay, so that's what you see. I mean, code given its parents and product of the children, which were S and H given their parents.
Professor, the variable flu is also involved, right? In the previous law?
Yeah, so the children's parents, right? So, yeah. I mean, that's okay. The reason I've written it this is because I've done some cancellation. In the denominator, also you will have that if you have a single factor. Let's say here. So if you actually count, then I'm saying is there are only 3 terms, right? But actually, that's because the additional terms will get cancelled with the normalization, because there was a normalization step. Remember here. If you do this normalization, it's going to end up that there will be some product, some term in the numerator and some term in the denominator. Okay. So essentially, what you're supposed to do is this, but by way of example, we didn't do that. But essentially, what remains is only these factors.
We could ignore the flu vector in that in case for this approach.
Yeah, you can ignore them because you actually ultimately have to normalize. Once you normalize, you will have the same terms, and those two will cancel because it's 1 by z times the whole thing. So that was the micro step in the Gibbs sampling. But what's happening? There's dependence, right? Going from a sample at 0th sample to first sample, I was using the values of the 0th sample, and that's why it's once you zoom out and go from sample to sample, it's actually a Markov chain. Okay, in the sense, I am drawing another sample effectively, let's say L plus 1 sample, given the L sample. Okay, and this, because I'm using the L sample to draw the next sample, it's these samples are dependent. Okay, and so what people actually do is run this loop, generate lots and lots of samples, and try to ignore the initial bunch of samples, and hope that the later part of the samples, although they are dependent, they are drawn from the distribution that you care about. We cared about drawing from the P of X, right? Where X could be whatever, 6-dimensional or 100-dimensional, something like that. And so one example of why this dependence issue comes up is because, let's say you have 2 random variables, okay? And it's such that, in the sense, these 2 random variables, let's say take, in this case, let's say they just take 2 values, just to be simple. And let's say there's a huge, okay, not 2 values because I'm doing something here. Okay, let's say the random variables take, let's say 10 values each. Okay, 5 values here, 5 values, 10 values on this side, 10 values on that side. Okay, but it so happens that the distribution, joint distribution, is such that it has no mass on these 2 parts of the graph. In the sense, let's say the probability of x1 is equal to 1 and x2 is equal to 1 is some constant. Same thing for all these other guys. But probability of x1 is equal to, let's say 1, but x2 is equal to 6 is 0. So what I'm saying is, if you look at the top view of this joint distribution, there is no probability in this region and this region. Okay. Then what happens is, since in the microsteps you are conditioning for the next coordinate value given the previous coordinate value, the other coordinate value, which actually, if you look at the diagram, let's say you start from here. Okay. Let's say here you're keeping x2 fixed and you're sampling an x1. It just happened that x1 is the next value, so you go to the right. Okay. Now you fix x1, so you're only getting a new value of x2, and x2 happened to be lower value, so you move to another number here. Similarly, now you fixed x2 and you sampled an x1, you got to here, because those are the 2 microsteps, right? But what happens is you can't go to the other side, because there's no way you can fix one and then go to the other side. Okay, so I'm just trying to show you an anomalous situation where the joint distribution is such that you can't really go from one part of the state space to the other. Okay, it's called state space, but you can just think of configuration. From one configuration to another configuration, it's not possible to go. Okay, because the conditional distributions are like that. And if you don't have this anomalous situation, it's called irreducible Markov chain. In the sense, if you can have conditional distributions such that, or you can have these conditional distributions such that you can go from one part of the state space or realization to another part of the realization easily, then it's called irreducible. And there's also an additional property needed, but if you can do that, then you are fine in terms of Gibbs sampling. Okay, and if you do that, then it turns out that that's a Markov chain, and that has a stationary distribution, which is the original distribution you wanted to sample from. And we'll get to this detail again in 2 slides. So what I'm saying is this is an anomalous situation where you can't jump from one region to the other, and therefore you can't do Gibbs sampling. Okay. Yeah.
Even if we start, like, let's say x1 is in the right side, the initial value of x1
Yeah.
on the right side.
Over here.
Yeah, over this.
Then the only feasible values of x2 are here, right? This region is the only feasible values of x. So you can't. So if you start here, then you'll just get samples from here. Let's say you're trying to find the expectation of x1. You only get samples from here. The expectation of x1 would be some number here, whereas the true expectation may be here, right? Something like that. Okay. Same thing with a less severe example is, let's say you have a Gaussian, okay, whose top view, you will take the top view of a 2-dimensional Gaussian. Maybe at 1 standard deviation, you draw this contour or edge, right? Now, if I'm doing the same Gibbs sampling, since it's 2 dimensions, a condition on one coordinate, sample from the other, a condition on the second coordinate, sample from the other one, I'll have these types of samples. So the samples are just vertices of this walk, okay. But if you actually see, if the actual 2-dimensional Gaussian is quite skewed, which means it's correlated, then you're not really reaching certain parts of the joint distribution at all, and so your expectation operation, or let's say you're estimating variance, it will be incorrect, right? Variance is also a function of the distribution, right? So those are the issues. Let's actually look at it in a little bit more detail. How many of you have actually looked at Markov chains before? How many of you have not at all looked at it? Okay. So you need to speak up and make me go slower, because in the class you can ask foundational questions, it's fine. So okay, let's try to understand what the Markov chain is here. Okay, why the name Markov even? We'll get to that actually. So let's say we want to sample from a multivariate distribution p of x, which is, let's say, 1 by z times some factors. Okay, that's why I've just distinctly represented the normalization and the factors. Okay, because for an undirected graph you need a normalization, undirected graphical model. And typically in undirected graphical model, we have already seen that z requires an exponential summation over all realizations of your random variables, right? So in Markov chain methods, what you want to do is, you want to sample from this, but you can't sample from there. So you want to now create something called a transition distribution. Okay. What is the transition distribution? It's just a conditional distribution. I want to create a sample x prime given a sample x. So if I can create this object, which given an x, it will create a sample x prime. Okay. If I can define this object somehow, and so if I define this object is doing what? It's going from an x value to an x prime value. So this could be a jump from a 6-dimensional vector to another 6-dimensional vector, another 6-dimensional vector to another 6-dimensional vector. So it's jumping from realizations to realizations, right? So for example, if I have 6 binary random variables, then it's 2 to the power 6 realizations that are possible. So I need to define this object over all those realizations, in the sense, what is the probability given the current realization I can go to any other realization? If I can define that, okay, that's actually a Markov chain. Is that clear? So yeah, so let's say this is 1 0 1 0 0 1. Okay, it can go to, in fact, 2 to the power 32 minus 1 other states, right? Let's say it's 1 1 1 1 1 1. Let's say there's some other guy which is 1 0 0 1 0 0. there are many such guys. If I can define, when I say I can define Q of x to x prime, all I'm saying is I can define all these transitions. Okay. Then it's a Markov chain because these are states, and you can transition from one state to another. Okay. And that's defined by Q. And it's Markov because given a state, I don't care from where I arrived to this state. So let's say I went from let's say I went from here to here to here in a one realization. Let's say I started from here, randomly figured out some next state to go to, randomly as in based on the Q. Okay, it's a transition probability. Then I figured out, okay, from this state I'll again use the transition probability to go to some other state. Okay. Now it's Markov because when I go to this other state, my probability of going to this state only depends on my current state. Doesn't depend on where did I come from. I could have come from 100 other different states before, but the current state is what just determines my next state, and that's why it's called a Markov chain. Chain because it's just a random walk, so you get a sequence of state realizations, right? Yeah.
How is it different from the previous one that we identified? So even there we are identifying a sequence.
Yeah, this is a Markov chain as well. This is a Markov chain method. Gibbs sampling is a Markov chain method.
So, but you mentioned that there's a burden phase, right, where it's not essentially a Markov chain.
No, it is a Markov chain, but it's not. So I just randomly specified a Markov chain. But how do we guarantee that the samples are from the joint distribution? We care about drawing samples from P of X, right? But here I just created some arbitrary Markov chain. Right? I'm just drawing samples from some random conditional distribution. I mean, of course, they are related to P, but why is it that if I draw from these conditional distributions, I will get samples from P? It's not
You
clear.
haven't done the exhaustive search that way.
No. It's just because what happens is after a long enough time, this Markov chain will have something called a stationary distribution. We'll define that, and that stationary distribution happens to be this. Okay, and because that happens only after drawing so many samples, the first few samples are not from P of X, are just rubbish. That's all. We'll get to what a stationary distribution is actually now. So if I define this object, it's just a transition probability matrix. If you remember, transition probability matrices. Basic transition probability matrix is from state S or state X. What is the probability of going to state X prime? Or the probability of going to state X double prime, and so on. It's just a conditional probability distribution. This object will be associated with something called a stationary distribution, which is represented by this equation. So a stationary distribution is going to be a distribution over the states of the Markov chain. Okay, and so it's a stationary distribution, right? So let's parse the term stationary and distribution. Okay, it's a distribution because it's a probability distribution. So sum over pi of x or x prime, sum over x prime, which are all the possible states as a 2 to the power 32 in number of pi of x prime is equal to 1. So that's a distribution. That's fine. Okay. Right. Even Q, when I wrote this. So when I write Q of x to x prime, this is actually a distribution. This is actually a distribution which is probability of x is equal to x prime given x is equal to x, whatever, x prime. This is that probability. So you can actually just enumerate it. It's going to be, for example, 2 to the power 32. Sorry. Why did I say 2 to the power 32? Yeah, 2 to the power 6, which is, what is 2 to the power 6? 64? Okay, 64 plus 1. So, I don't know why I said 2 to the power 32, but it's 2 to the power 6. Okay. So, Q of x to x prime is just probability of going to some specific realization x prime given the current state of x. Okay, that's why it's a conditional distribution. It's a distribution, so it will have 64 numbers with sum up to 1. Okay. Q is that, and pi is also a distribution. pi is not conditional distribution, it's like a marginal, right? So it's just probability of phi of x is just the probability of x taking value x. And okay, and we just want to design this transition probability matrix such that phi of x is actually equal to the p of x, okay? Because p of x is also just a distribution over my states. Pi of x is the stationary distribution determined by this object, right? The transition probability distribution. And I just want to construct this such that these two are the same. And why call it stationary? Because when I'm going from a state to a state, I actually need to index it in terms of time, right? I mean, I start from some sample. Let's say I start from x0, okay, x superscript x0 sample 0. Then I look at this table. This is just a table, right? This, it's a table with each row x row saying from x where all can I go to? Let's say x prime, and that would be maybe this column x prime. So each row is a conditional distribution. That's why it's a transition probability matrix. Okay. Now, if I go from x0, let's say from x0 I went to some other sample x1, and again another sample x2. I'm actually using the index. Let's say index of sample index of time. So pi at time t. Pi of x may need a time indexing. It happens that you don't need time indexing. That's why we call it stationary. Okay. We'll get to we'll again redefine this. We'll investigate this a little bit further. But stationary just comes from there is no time indexing. Although I'm starting from some time, let's say after 100 units, 100 steps or 1,000 steps, this stationary distribution doesn't depend on the index of time. That's why. Okay. So let me redefine these terminologies. Transition probability is this probability from one state to another state. In this case, realization of random variables or realization of random variables. Pi is supposed to be so this is a different quantity than the stationary random variable. It's pi t of x. So it's just a probability of reaching a particular state x or a realization x after t steps. Okay. It's just start from whichever state you want to. Tell me what is the probability of reaching after 100 steps. The probability of reaching let's say particular state x prime. Okay. So that's what pi t of x is. Occupancy probability. And pi t defines stationary distribution pi of x if you choose an appropriate choice of q. Okay. So what I'm saying is pi t of x just converges to pi of x after some time. So you kind of ignore pi t of x in terms of practice. And pi of x, okay. So pi of x, when you get pi of x, which is a stationary distribution, it's called the equilibrium, and there's a bunch of conditions that you can define which lead to that equilibrium. In the sense, when you have an equilibrium, in the sense pi t of x is, you can drop the subscript t, then you have reached you have gotten the stationary distribution. At those time steps, you have reached an equilibrium condition. In the sense that if you take a step, you will get to another state x prime with probability pi of x prime. Okay, the transition probability kind of becomes irrelevant. So at that equilibrium state, so that's the equilibrium, and there are some conditions you can define about this transition probability which can guarantee that equilibrium. If the conditional probability or the transition probability object satisfies that some condition or some equation, then you will reach the equilibrium. Okay, that implies equilibrium or something like that. So what's the big idea? The idea is Gibbs sampling is defining some transition, right? These transitions, these micro transitions leading from one sample to another. It happens that this particular transition probabilities satisfy the particular condition which is called the detailed balance condition. Therefore, that leads to an equilibrium, and that equilibrium is P of x. Okay. They satisfy a condition which leads to an equilibrium, and the equilibrium is characterized by pi of x, which is equal to P of x. In the sense, the guaranteed equilibrium which is pi of x. Okay. Which is P of x, which is the original distribution that you cared about sampling from. Okay. So let's say pi t of x is the probability of being in state x at time t, and pi subscript t plus 1 is the probability of being in state x prime at time t plus 1. So how are these two related? It's quite, so this is more informative, I guess. So probability of being in state x prime at time t plus 1 is just start from any state. So this summation is just saying start from a state x, what is the probability that I am in state x at time t, and what is the probability that I am going to transition from x to x prime. Okay. So there is a recursive definition for these pi's, occupancy probabilities, right? So stationary distribution just means that pi t is equal to pi t plus 1, in the sense there is no dependence on time t. And you can just substitute that pi over here, you will get pi of x prime is equal to sum over whichever state you start with, take a transition, and that summation over all x's is going to be still pi of x. So it's like pi is satisfying both sides of the equation, right? So what is the detailed balance equation? Detailed balance equation is pi of x. So start from a state x with some probability pi and transition to another state x prime with probability q of x prime given x. That should be equal to the probability of starting from state x prime and coming to state x. Okay. So that's just called detailed balance equation. And this equation implies stationarity, in the sense if a q object satisfies this equation, then pi is the stationary distribution. Okay. So remember what we were trying to do. We were trying to define a q. Okay. We wanted to sample from p. We are trying to define a q. As long as we can ensure that q and p satisfy this equation, I know that for that q, that p is the stationary distribution. Right? Is that clear? So our decide pi is the p of x. Okay, we want to sample from p of x. If I can define a q such that q and p satisfy this equation, I know that p is going to be the stationary distribution. So when I run the Markov chain, eventually I'm going to be sampling from the stationary distribution, and so I'm going to be sampling from p of x. Okay, let's skip the detailed balance, how Gibbs sampling obeys the detailed balance equation. We'll skip that for now. We'll get to a couple of other methods which we'll not go into the details of, but are also popular in the Markov chain Monte Carlo family of methods. In fact, one method which is called the Metropolis-Hastings method. Okay, it's important to kind of at least understand how it's constructed or how it is executed. The underlying reasoning of why this makes sense again ties back to the detailed balance equation. In a sense, this particular way of going from x0 to x1 to x2, like in Gibbs we were doing some micro steps, in here we will do some other steps, but they will all lead to a detailed balance equation which will lead to the proper stationary distribution, which is p of x. Okay, and there are many other methods. We will not get into all that. Okay. So what is the Metropolis-Hastings way of generating dependent samples? x0, x1, x superscript 1, x superscript 0, x superscript 1, and so on. Is you start from, let's say, some sample x. Let's say you start from some sample x. Okay. Then you're gonna sample another. You're gonna sample another x from the conditional distribution, because the object that we have is q, right? Here we are just calling it q tilde, but it's the same thing. We have this q, so I have written somewhere. We have this q. We're gonna draw a sample from this. Okay, we have that candidate. Now we're gonna put that put that sample in our basket of accepted sample, or we're going to reject that sample. How are we going to do that? Because we sampled from Q, but we can also evaluate Q of x prime given x, because we sampled from that and we can just read off the entry from that transition probability matrix, right? Whatever that number is. We can also do the symmetric thing. We can read off the probability of x given x prime. There is no sampling involved here. Just read it off from the table. Okay. Those two numbers we can read off. And P star, if you remember, is just the numerator of that joint distribution. So there's no z term, which is a partition function. So the numerator for a given x is just product. Look at the tables or look at the functions and just multiply. So we can compute P star of x prime and P star of x. Okay. Now with those four numbers, we're just going to compute another number, which is going to be a of x prime given a of x prime comma x, because it just depends on these transition probabilities and the P stars. Okay. So this is some number, and the min operation is just saying that this number should be is positive but less than 1. That's all. Okay. Now with this number, you're going to flip a coin. Okay, let's say this number is 1/2, then you're going to flip a coin with bias 1/2, and if it lands head, you take x prime in your bucket of the next sample, which is it's a valid sample. If it lands tails, then you ignore that sample, and again sample another x double prime from this transition probability and just do this check. Okay, that's it. That's Metropolis Hastings for you. Any questions about how you're going to compute?
Could you repeat this step?
So these are all computable, right? Let's say I have a sample x. Okay, let's say x naught, x superscript 0. I want to create another sample x1, right? So I'm going to generate x1 from just looking at this Q. I'm going to just sample x1, x prime. I have that candidate now. Now I'm going to evaluate a bunch of numbers. These are nothing to do with sampling. I'll just evaluate what is the Q of x given x prime from this table, Q of x prime given x from this table, P and P star of x prime and P star of x, right? I'll just compute this A. That's just going to be a number between 0 and 1. First of all, it's positive because all these numbers are positive. Okay, assuming there is no division by 0. But these numbers are positive, so I'll have another number A. So I have this candidate and I have this number A, which is between 0 and 1. I'm going to flip a coin with that bias. Okay, and if it lands head, I'm going to take that sample as my correct sample. And if it lands tail, I'm just going to ignore this step and again draw another x prime and do the whole thing. Okay, and Metropolis sampling is the same thing as Metropolis Hastings, where you have a symmetric transition probability matrix. Q of x prime given x is the same as Q of x given x prime, so you get rid of those additional factors. So it's a simpler thing. Okay, but the same as before. So this is Metropolis Hastings family of sampling methods, and these are also actually this two-step process of drawing from Q tilde and accepting or rejecting it. That two-step process defines a meta or whatever Q object, that Q object, whose stationary distribution is going to be our desired P of x. That's it. Okay. To wrap up, we looked at representation inference, and today we're going to look at learning, which is going to be either the parameters or some other quantities. We'll see. So, any questions so far with respect to sampling? Okay, let's look at learning. So, learning has a lot of variations. We have 10 more minutes. Okay, learning has a few, has a bunch of problems that you can actually do learning, and so these problems are all different than what the learning type of problems that you saw in the first few lectures, which is classification or regression and stuff. So here we want to learn a few things. So we'll see what all we want to learn. It could be, okay, there are two major things that we could learn. One is the parameters of my joint distribution, which is going to be the entries of my conditional probability table or the entries of my factors, right? If you remember, in a three variable graph, I had 3 factors, let's say 3 cliques, 3 factors, which had 4 numbers per factor. How do I learn those numbers from data, right? So those 12 numbers, how do I learn? Or the other thing is, how do I learn the graph itself? Why should there be an edge between 2 random variables, right? So given those 2 objectives that we want to learn, there are many variations, right? First of all, we studied directed and undirected graphs. There could be several situations you could be in. First of all, you may know the structure of the graph, you just want to learn those numbers in those factors, right? Or you don't know the graph itself, you just have a bunch of random variables. So you need to learn the graph and the parameters. You may have complete data, in the sense you may have every sample that you have may have all the six coordinates realized and observed, okay? But you may have some other types of data where some coordinates are missing at every in every sample, or in some other versions you may not even observe some random variables, okay? You know that such a random variable exists, something like quality of let's say quality of a product, it's not exactly observable, but it is, you can conceptualize such a random variable, right? And there is also this distinction between generative and discriminative. It just means whether you're dealing with joint distributions or you're dealing with something called conditional distribution. So this is not very much big of a difference, except there's something called some technique called conditional random fields, which are essentially discriminative versions of a discriminative graphical model. So we'll get to that towards the end. Okay. So let's look at the first variant. Let's say we have a directed graphical model, we have full data, and we know the structure. We just want to fill those factor or the conditional probability tables, right? This is going to be quite simple. So let's go through an example. Let's say we have a directed graph which has 3 random variables. Okay. So what do we need to learn? We need to learn this number, this number, this number, this number, and all these numbers, right? That's the learning problem. Any question with the objective? Okay. And what do we have? We have training data, which is just a collection of example assignments to the random variables. So in this case, there were 3 random variables, so 3 assignments, right? 3-dimensional assignments or realizations. So let's say you have 100 of them. Using those 100, you want to fill in those 8 plus 2 plus 2 or something like that, those numbers. Okay. So let's be more specific. Let's start with just one random variable. Okay. And this should be familiar to you guys. So if you have just one random variable, let's say it's a rating of a movie. Okay. Movie rating can be between 1 to 5. Okay. So one random variable is a really trivial graph. It's just one node, right? Now I want to learn the probability of that random variable taking a particular realization, right? So to represent this probability has just one factor, and the factor has parameters which I'm representing as theta, which are just going to be p1, p2, p3, p4, p5. Okay, which is just the probability that r is equal to 1, probability of r is equal to 2, probability of r is equal to 3, and so on. In fact, I don't need 5 parameters. Why is that? Yeah, it's a distribution, so we don't need p of 5. P of 5 is just 1 minus sum of those 4. Okay, let's say this is our training data, which is 1, 3, 4, 5 4s and 3 5s. Learning is just about turning the training data into some numbers for this theta. Okay, some numbers for these parameters. And the intuition is that probability of r is just going to be proportional to the number of occurrence of the realizations r in my training data set. And so given these numbers, I can just fill in the probability of r to be these. For example, 4 appears 5 times in this 10 number sequence, so 4 is 0.5, right? So this is it. This is one complete run of a learning step, but that's because we had a trivial graph which is just one node, right? So what do we do with 2 nodes and we have directed probabilistic graphical model? So 2 nodes, it's a directed graph, all the variables are realized, so and the structure is known. Let's say the structure is precisely this way. Okay, the edge of these 2 random variables. So what is the 2 random variables? Let's say G is a genre and R is the rating. Okay, so genre is the is two values. Okay, drama and comedy, and R is 5 valued as before. Now we know that given this graph, we know there has to be, since there are 2 random variables, 2 factors. We know what the factors should be. In fact, the conditional distribution here and the marginal here. Let's say we have this training data. So both observations, both random variables are observed, and we need to, the parameters are going to be P of G and P of R. I've just succinctly represented here. So P of G will have, 2 parameters or 1 parameter, so 1 parameter essentially, and P of R will be the conditional distribution. So we'll count the parameters in the next slide. So what do we do here? It's similar to what we did with just one random variable. So estimate each local conditional distribution separately. Okay. So for each value of the conditional variable G, conditioned variable G, estimate the distribution of R. Okay. So because we got P of R given G, right? So for every given value of G, R can take some number of values. With this data, R is only taking, for a given value of G, R is only taking value 4 and 5. So it's split as 2/3 and 1/3 out of the 3 values that it's taking. So R being 1, 2, 3 is zeros. Okay. So those are my estimates. Okay. This is again another full complete learning step. We have gone from data, given the directed graph, we have computed the parameters. Okay. Now let's look at 3 variable example. That's again G is genre and A is award 1. So A is a binary random variable, it's 0 or 1, and then given the genre and the award, R is the rating. Okay, and given this graph, we have this factorization, and let's say we have this data. What do we do? We have already seen 2 examples, so it should be clear what we do, right? We can just look at how many times G took a value small g and A took a value small a, and just compute this, right? It's just counts, normalized counts. It's fine, it's intuitive and it works. Let's say we have a different graph where we just have one random variable corresponding to genre, but we have multiple ratings now. So 2 ratings, okay? So now the joint distribution is this. This is again decomposes. This is a tail-to-tail relationship. But anyway, this decomposes in this way, right? And let's say we again have a training data, which is going to be the genre, and what was the rating of the first person, what was the rating of the second person. Okay. Now here we can actually see that maybe these different users are not really different users with different distributions, but they may be the same user who is rating by drawing from a distribution, and that's the idea of parameter sharing, which just means that the conditional distribution of R1 given G is the same as the conditional distribution of R2 given G. Okay, which means that I'm saying there is no distinction between the first user and the second user. Okay, and this reduces the number of parameters, right? Because previously I had for every user I had I was supposed to create these conditional distributions, but now I'm just creating one conditional distribution. Okay, so, which is P of R given G, and the way I'm going to fill this table is just the same as before. I'm just going to count for every, let's say, the 2 values of G, which is comedy or drama, how many ratings were 1, how many ratings were 2, and so on. Just counts. And that leads to the general algorithm, which is just the same as what we were doing before, which is we have training data of full assignments, right? And we want to compute these parameters, which are essentially the descriptions of these conditional distributions. And so what we'll do is for every data point in my training data, for every variable, I'm just going to count, increment the count of that factor or that conditional distribution which includes that variable. Okay, so I'm going to maintain a count with this as the index, as in some triplets or something like that, and I'm going to increment the count whenever that variable takes a particular value xi. Okay, and then I'm just going to normalize it. So for each factor and local assignment, which is going to be x parents, so I'm going to set p of xi given x parents to be proportional to that count. That's all. In fact, what I'm saying is you have these counts, just think of those counts as proportional to the conditional distribution. That's what we did previously, and so that's it. That's essentially what is called maximum likelihood for directed probabilistic graphical models. Okay. So we'll break now, and we'll get back to maximum likelihood in general in a couple of minutes.
Do we email our new proposal to you and the TA or just the TA?
I just literally, it's like,
Oh, did you?
I like it's both of us are working on it, but TA has the more responsible is the responsible person in this group
Okay.
with respect to the assignments and the projects. So
Okay, cool.
I just had one small doubt.
Yeah.
The transition of x to x prime and x prime to x, isn't it same, the value?
no, it's just need not be the same, right?
It
You can ascribe arbitrary
but
numbers.
if we go from one state to the other and we want to go back to the same state,
Doesn't have the same, right? Like for example, let's say it's a two node. It's a state S1 and state S2. This could be 0.3. I can go to S2 with 0.3 and go back to S1 with 0.7, and this could be 0.4. Going to S1 to S2 would be 0.4, and S1 to itself would be 0.6. This is a simple Markov chain.
what is the value that influences this to be different?
No, I just define. So you just have to define Q of x to x prime, right? I just defined it from S1 to S1, S1 to S2, S2 to S1, and S2 to S2. I just put some numbers
This
here.
is what we are defining, but we have to calculate.
We are defining. No, we are defining such that this should imply that pi of x is equal to p of x. So our objective is to define this such that pi of x is equal to p of x. In the Gibbs distribution, we are not explicitly defining this. We are just doing that micro steps. But that micro steps actually define something like this, which actually leads to p. I mean, that is just analysis which we skipped. One slide we skipped.
Thank you.
Maybe
Yes.
it's a very basic question.
Yes.
I was just reading one. So, after doing all these things, so are we trying to achieve to understand the state of a particular? So, for example,
No, joint distributions can be used for everything. Prediction,
anything.
anything, any computation that you want to do always has the joint distribution in it.
So, I mean, tell me whether I'm thinking in the right way. So, you have a data set with you. Say, for example, sunny day or a rainy day, and you're going to predict the 30th day's situation.
Yeah.
And so you draw multiple samples from your data, and you connect it to the next day, and that will be the transition.
No, the sampling is just for inference.
Right? Okay.
That is just to compute some number of the joint distribution.
Okay.
That is not directly related to the prediction yet.
Okay.
Once you have the joint distribution, okay, sorry. What is the question?
My question is like, so the sampling is done. Yeah,
Sampling
exactly.
is to compute samples from the joint distribution. Using those samples, if you want to make a prediction, you can.
Okay. So basically, how these, for example.
You have this. Let's say you want to. Let's say you have P of x. So x is actually x1 to x2. Let's say to make a prediction of I need P of x1 given x2 to x10. For example, like in this call, this x1 is just renaming a variable. You can think of this as feature vector. This is the class. It's asking what is the probability of the class given the feature vector. Compute this. I need samples from this distribution. Right? I can just draw y1, y2, y3 or something like that. And I can just look at which one is the majority and just call that as a majority. I can do prediction given. If I have joint distribution, I can do anything. So this is like even better than the stuff that we see in the first part of the class, which was just models for this. But just directly doing this as a f of x, where that f was so if I have this distribution, I can sample from this and say what the function is. Given any x, condition on any x, I can sample from this distribution and tell you what the function is. And this is better than this one. If you have this. We'll get to that graph. Maybe okay, we'll resume. So what is maximum likelihood? This is one of the most important piece of technique that you should know in your toolkit. Maximum likelihood is known in econometrics and in statistics for estimating functions of your distribution. So maximum likelihood is doing all just this, right? Let's say you have 10 examples in your training data. Okay, your training data has 10 tuples. Then maximum likelihood is all about finding the parameters, maximizing the parameter, figuring out a parameter such that the product of these probabilities of probability of x is equal to x, little x, given the parameter for each of your, and the product is over each of your training example is maximized. Okay, that's maximum likelihood. Why is it called likelihood? Because it's the probability of the data given parameter. Okay, and all you're trying to figure out is the parameter. Your data is already given, you just want to figure out the parameter. Okay, so how does maximum likelihood look like? I mean, we have already seen how it looks like because we were computing counts for individual conditional distributions, right? So for example, if you had probability of the genre, in this case probability of genre being, let's say in this case the data was d comma 4, d comma 5 and c comma 5, let's say, then you just probability of G is going to be probability of the genre is going to be probability of D times probability of D times probability of C, right? Because D and C, right? Probability of R is going to be the rating is going to be 5. In this case, there is 1 5. One second. Yeah, sorry, it's 1 5 given C and there are 2 Ds. Okay, so it's basically I'm just expanding out the product, so this is what we have seen already intuitively, so let's not focus on this particular formulation. So for Bayes networks or directed probabilistic graphical models, the computation of the parameters is kind of easy, right? You just focus on each factor and you can just use counts and normalization to get to these numbers. But what do we do if you have missing data? So you have the directed probabilistic graphical model, you have the structure is known, so the edge directions are known, but the data is incomplete. Okay. What do I mean by that? When the data is incomplete, let's say we are in the case where we have something called latent variables or hidden variables. In the sense, you never observe that random variable. Okay. In this case, the genre is never observed. Let's say. Okay. Because that's not an explicit thing that you can ascribe. You're getting ratings, but you don't know which genre it is. So then you'll have one coordinate of your realization as unknown in your data, right? So this is essentially an instantiation of incomplete data, right? So let's say H is hidden and E is observed. So let's say E is a random variable which takes a value E and is observed, and H is a random variable which is hidden, in the sense it's not observed. Okay, not at all observed in your data. And now you want to figure out, let's say in this case is H is D and E is the two ratings R1 and R2, okay, which were 4 and 5, let's say. Now you want to find the probability of, so you still want to find the parameters theta, okay. It's the same expression as before, the maximizing the likelihood, except that now you don't know what value H took. So you're gonna find the summation of, it's the probability of data. So okay, because we don't know the because H is hidden, we're going to maximize the likelihood of the marginal distribution. In a sense, marginalize such that the hidden variables are gone, and that's what is this expression. So previously we had the same. Previously we had this without the summation. So we had the probability of the data given the parameter, where if H was observed. Now H was not observed, so let's marginalize it out, and it's called maximizing marginal likelihood. Okay. And how do you do this operation? Okay. Previously, when we observed H, we kind of use counts normalized, and we know how to get the parameters theta. Right. Now, if you don't have H, then it leads to a very interesting algorithm called the expectation maximization family of algorithms. This family of algorithms. And the inspiration is from the k-means technique. So if you have taken 572, you must have seen k-means algorithm for clustering, right? So what is the algorithm? So let me first describe the algorithm, and then I'm going to intuitively try to describe how it's related to k-means. Okay. So as I said, H is hidden and E is observed. Let's E is observed to be some small case E. Then expectation maximization is a name given to this algorithm because of two steps. There's going to be an expectation step and a maximization step, short form to be E step and M step. The expectation step is going to be computation of marginals over the hidden variables. So in this case, let's say there's one hidden variable. So I'll compute some distribution Q of H, which is going to be probability of H is equal to some realization H, small h, given my observed random variables and theta, right, for each H. And then I'm going to create, this just means I'll just use this Q of H, okay. Now, what's the issue with this E step? I need to know theta to actually compute Q of H, right? But what I'm going to do is, let's say I start with some random theta. I'm going to assume that theta is the correct theta and compute Q of H, okay. Then I'm just going to go to the next step, which is I'm going to compute the maximum likelihood, actually not the maximum marginal likelihood. I'm going to compute the maximum likelihood to get another theta, new theta, okay. Because is both steps clear? I'm going to use some arbitrary theta to get a Q of H. I'm going to use Q of H to get to some new theta. I'm going to use that theta as a part over here and get new Q of H. With that Q of H, I'm again going to get theta and so on. Why is Q of H required? Because with Q of H, I can actually find the joint probability. Okay, given the marginal, which is going to be the hidden variable here, H, I can compute the joint probability. Okay, so let's again try to understand. Let's go from k-means and then again get back to EM. Okay, so EM tries to maximize marginal likelihood. That was the original objective, but the way it does it is different, right? The way it's doing it is that it has 2 steps and it does something in each step, the E step and M step. But let's so is the objective and the algorithm clear in the sense of the objective was to maximize marginal likelihood, which was this, okay? Because hidden variables are not even observed, I just want to maximize the data that I observed given theta, and I want to figure out the theta, okay? This is actually just the same as this. I just marginalize over the hidden variables. So this is what I want to maximize. I'm doing it by proposing an algorithm which has 2 steps. Okay. In the second step, it is maximizing likelihood, so it's different from marginal likelihood, but it's okay. It's an algorithm which is doing something. Okay, right? So the algorithm is trying to maximize marginal likelihood, and k-means is actually a special case of EM, and actually it's related to something called Gaussian mixture models. I don't know. Have you seen Gaussian mixture models in the business data mining course? No. Okay. It's not needed here. So what is the objective of k-means? The objective of k-means is to estimate cluster centers, right? You have clusters. You want to figure out cluster centers. K is fixed. Let's say k is 10. I fix some k. I want to, given let's say 2-dimensional data, I just want clusters. Let's say. You can visualize that, right? How do you do that? You don't know which points belong to which clusters. You know, that's the whole problem. So you take an alternating optimization approach. You first find the best cluster assignment given the current cluster centers. Randomly pick k points to be the cluster centers. Then figure out the best cluster assignment to these cluster centers, right? That would be a cluster assignment. Now, given those cluster assignment, you change the cluster centers given this assignments, right? That's the 2-step procedure in the k-means algorithm, right? This should be clear because it's not content of this course prerequisite. So what do we do with EM? Okay, EM is very similar. It's again alternating optimization. So here we don't know the hidden what the hidden variables are, or in the sense the distribution of the hidden variables basically. So we compute the distribution given the current parameters. So probability of the hidden variable given the current parameters, as well as given the evidence, which in this case is the data. But to do this, we will need inference because this is computing the probability of a bunch of random variables given some evidence. So this is precisely what we have been dealing with in the whole inference part, right? We can use various propagation or Gibbs Markov Chain Monte Carlo methods. And this distribution will provide, let's say you computed this conditional distribution. Let's just rename it as Q of h. Okay. So this Q of h is going to provide a number, basically. It's a distribution, but it just provides a number to every value that h can take. Right? It's a value between 0 and 1, and maybe it sums to 1. That's fine. It gives a number to every value h can take. Okay. It's just a temporary variable that will be used in the next step. But so what is it doing conceptually? The E step is generating a set of weighted full realizations or configurations with weights Q of h. Okay. You can think of what the E step is doing as I have E, I don't know h. Okay. I'm going to say, okay, what all values can h take? Let's say h is a 3-valued random variable. Okay, can take h1, h2, h3. Then I'm going to say h1, e will have a weight Q of h1. h2, e will have a weight of Q of h2, and h3, e will have a weight of Q of h3. Okay, that's what the E step is doing. Because I don't know what should be the what the hidden variables realization is, I'm just gonna use all these numbers. Okay. And in M step, I'm just gonna do maximum likelihood estimation. Okay, which is what counting and renormalizing stuff that we were doing in the examples to estimate the parameters theta. Okay, thetas are part of your joint distribution expression, right? So thetas can be estimated if you have Q of h. Okay, the weights. In a sense, E step has actually created additional data for you because it's telling you h up, h comma e appears, but it's just tagging on a weight q. Let's say Q of h, for 3 valued random variables, case be 1/3, 1/3, 1/3. It's as good as saying one instance is h1 comma e, one other example is h2 comma e, other example is h3 comma e. With that data, you can estimate parameters, right? you can just do maximum likelihood. Okay, and if you repeat E step and M step again and again, eventually you will converge to a local optima. Converge just means eventually it will not blow up. Your optimization, whatever you're repeating the steps a lot of times, you won't get numbers which are running off to infinity or something, or running off to 0 or something like that. You'll converge to something reasonable. It's a local optima. Local optima because actually you're supposed to do this maximization. So if you can't get to the optima, you may at least get to the local optima. Local optima means locally at least you can't improve. Okay. So that's EM. Here's an example where let's say you started with some parameters. Okay, I have some parameters right now for some parameters in the sense that joint distributions parameters. Okay, the E step is gonna look at the data 2, 2, 1, 2, and it's gonna fill in these missing entries, these question marks. With in this case the hidden random variable has only 2 realizations possible. So C and D and C and D. For each one of them, it's gonna compute the probability of G given the evidence, right? But that is actually proportional to the joint distribution, right? We just saw that the conditional distribution is just proportional to the joint distribution, and so we'll get these numbers. We know this joint distribution from this table. We can compute that. So we get these numbers, and Q will be just normalization of those numbers. That's all. Okay, we are not doing Willy propagation or variable elimination because you can actually just enumerate this. That's all. Otherwise, we can do BP or MC or something like that in this step. That's where you need inference, and that's why we spent a lot of time on inference, because learning will need inference as a subroutine. And in the M step, once you have these Qs, you just increment the counts. In this case, for G, you just increment the parameters P of G and P of R given G appropriately. So that's because of these weights that we are adding these Q of H's here, but we can it's basically scale counts. That's why it's like this. So given from data, you can count the number of times. Let's say here probability of C and R happening together is 0.5. C and R is equal to 2 happening together is 0.5 plus 0.69 plus 0.69. So it's straightforward to increment the counts. Okay, given the new data, which is augmented data, and augmented data, you can basically do the count and renormalization here. That's what's happening here. Okay. Yeah.
So will the optimal solution depend upon the initial value of theta we take?
Yes.
If we take something which is not reasonable, we will not.
Yeah, it's same issue with k-means, right? So with this method, you will have to do the same thing with k-means. In k-means, you start randomly with random 10 different runs of random cluster assignments, and you ultimately converge to the cluster assignments, right? After a lot of times, then you will do some averaging or some aggregation of those results. Same thing here as well. So you will start with different EM original parameters, do all your EM steps, and then kind of learn the final parameters. Okay, as an average or something like that. So which is computationally more expensive for at least directed probabilistic graphical models? Probabilistic inference given the parameters, how hard is it? No idea. Probabilistic inference given the parameters is easy. Okay. Not exactly easy, but inference we've just dealt with inference in the previous lecture and this lecture, so we know how to do inference given the parameters. But to learn the parameters given fully labeled data is actually easier, right? For Bayesian networks or under directed probabilistic graphical models, learning the parameters is just count and normalize, right? But if you have if you have missing data, then you need inference as a subroutine, and then you have more computational complexity, right? Okay, let's look at and the people have tried to study estimation of parameters. Right now, you can also say I have this data, my Excel workbook or something like that. Now I want to create a probabilistic graphical model. How do I do that? Right? In the sense, I'll first at least have to create the graph. Right? I want to create edges between nodes. The columns of my Excel sheet can be the random variables, but I need to create the edges of those. Create edges between those random variables, and that's this set. I want to create a directed graph, and I don't know the structure. So, let's start with the basics. Let's say given data, which model is correct? So this is a model. This is a model, right? This is a model which doesn't have any edges. This is a model which has edges. And there is no really very good answer here. We start with we just want to answer which model is more likely, and so let's say we have a prior that okay, this model is more likely than this model. Okay, some belief which is encoded as a probability value. We have this data. We can just given the data, we can figure out what is the probability of model given data. It's like a posterior, right? In Bayes rule, I have a prior. I've been given data. I want to predict the probability of the model given now the data. Maybe given the data, it's clear that there has to be an edge between. There is a dependence between x and y. Okay. Then your numbers would kind of get updated. Okay, it's just Bayes rule. And once you have these numbers, you can do model averaging. If you want to do any other inference, once you have the edge or the structure, then you can kind of keep all of the models and do averaged results, right? Or you can also pick one of the models as a likely model based on your domain knowledge or something like that. So it's really not a very there are a lot of design choices in between. Okay. So what was the probability of model given data? That's, as I said, was Bayes rule. So probability of model given data is just probability of model, which you can assume to be, if you have two models, I can just assume I don't have any prior, so I'll just assume 1/2 or something. And what is the probability of data given model? Okay. So what is a model? Model is this thing, right? This is a graph. So it's not really parameters, right? So you really have to find probability of data given model by actually doing an integration. So for a given model, fit all the parameters that you can. For every, there will be a probability of a parameter given the model. Okay, fit all the parameters you can and predict and compute the probability of data given that parameter. Okay, and then integrate or basically do an expectation over that to find the probability of data given model. Okay, it's just trying to say how do you, because model doesn't have parameters by itself. So the graph itself doesn't have parameters, but the graph specifies, for example, a joint distribution. In this case, probability of x times probability of y given x. So two parameters. Here it's just probability of x times probability of y. So again, two parameters but different. So for every possible parameter number that you can put in, what is the probability of the data? You just sum over all possible parameter values that you can put in, and then you can evaluate the model itself, the graph itself. Okay, it's I would say this is more choice driven and so more heuristic in nature. So, but still you can use it if you have additional prior knowledge about how the random variables are related to each other. So what we've seen is for directed graphical models, you can use prior knowledge hopefully, or even the structural learning part to create these edges or create a graph. You can use the data to fill in the conditional probability tables. That's essentially what we have done till now. And to fill in the conditional probability tables, we can use maximum likelihood, which is just count, normalize. For these, the maximum likelihood for this is simple, but maximum likelihood in general for any arbitrary problem is is problem dependent. Okay. So let's now look at undirected probabilistic graphical models, and we'll look at something called generative version, which means we are just going to look at whatever we have seen so far. Okay, those were the generative versions. So just to recall, what was the undirected probabilistic graphical model setting? You have a bunch of random variables, in this case 4. You have undirected edges, and you have a probability distribution, which is just going to be a product of cliques, right? And the partition function value will just be a summation over all realizations of the numerator. Okay. So, for example, a single clique, let's say in this case, what is S, smoking and cancer. Let's say they are binary random variables, and this is the factor, okay, or a potential function. So how do you learn? So one interesting transformation that you can do is, instead of defining factors directly on the random variables, instead of defining factors this way, which are just products, we're going to define, we're just going to take an exponent, exponentiation of the terms. So this is exponent of the sum of a bunch of numbers is just the product of those numbers, right? Where is it? I mean, is this clear or should I write it? Okay. Yeah, e to the power a plus b. So if you think of these as the phi's as before, right? Then that's all we have done here, and we have explicitly required that the let's say phi of s comma c to be equal to e to the power w. Let's say in this case, let's say wi times f of s comma c. I mean, the I is indexing is not necessary, but what I'm saying is, instead of defining a function like this, I am requiring you write a function f such that this phi is the same as this. I have additional weight here, but it's just a parameter. I mean, there is no improvement here. I mean, it's just saying, factors are factors. I'm just going to write factors as in a log linear representation. Okay. So in undirected graphical models, especially undirected graphical models, we still do maximum likelihood. So maximum likelihood is still going to be maximize over theta, or the probability of my whatever data. Okay, which is just probability of x. X is equal to x given theta, and you can do a product because let's say you have 10 examples or 100 examples. Let's say I is equal to 100. So the same as this. I mean, this is the maximum likelihood problem. Okay. Now, like count and normalize stuff that we were doing in the directed probabilistic graphical case, we can't do that here. So we'll have to resort to numerical optimization. Which just means, remember from the first second class we were doing back propagation, which is basically first order method or stochastic gradient descent. Here we have to do gradient descent. Okay, so if you actually, so this is your objective. Okay, the parameters are just explicitly defined as parameters. So you can take. What happens is you can actually make. You can actually think of these. When I write phi in this way, okay, I can just ensure that w is the unknown parameter and these are fixed. Okay, these can be just indicators of each entry of each row of the. Where is it? These can be entries of each row of this connection probability table. Okay. What I'm trying to say is that this reparameterization of the factor lets me write my factor parameter to be just wi. Okay. For example, what I'm saying is I can write e to the power w1 times indicator. So this is a symbol. Indicator of smoking is equal to 1. What is this? Cancer is equal to 1. Times e to the power w2 of indicator. Indicator just means if this is true, then that's 1. Otherwise, it's 0. So s is equal to 0 and c is equal to 1. That's it. and so on. So there are 4 cases. So I basically have 4 parameters, right? It's the same as before. You agree? How many of you are not following what I've written? So if this condition holds, then I'll have a parameter w1, e to the power w1. If this condition holds, I'll have a parameter e to the power w2. If this condition doesn't hold, this is 1. So it's not a parameter anymore. So only when, like, for each row is basically an assignment, right? Is a realization. So given a realization, I'll have a parameter. So that's just a way of defining the parameters, right? So what I'm saying is every coefficient in my expression is a parameter, and only those are the parameters. Okay, these are just essentially not parameters anymore. And so when I take the derivative of the log of my objective, okay, let's ignore the product because product is it's basically you'll get a sum. So you can ignore the product. The product is over each example that you have. Okay, let's say you fix one example. Then if you take the derivative of the weight with respect to the product, okay, log of the objective, you'll get if you take the derivative with respect to w1, you'll get this indicator, right? But you have lots of data, then it's just going to be the sum because I took a log. This is going to be sum. So it's going to be the number of times feature I is true in data. Okay. Or for or for a given example, whether the feature I is true or not. Okay. That's what it is. What I'm trying to say is I'm trying to create these derivatives, and I'm just trying to kind of motivate gradient descent. Okay. I'm not even going to go to the gradient descent. I'm just saying this is the objective. We can't do count and normalize as we were doing in the directed probabilistic graphical case. So we are just going to take the derivative with respect to its parameters and do gradient descent. Okay. But to do gradient descent, we need to compute this term. Okay. It just so happens that the gradient of the objective with respect to, let's say, parameter wi is something that we can compute from just data. Okay. This is just 1 or 0, or if you have data, more data, it's the sum of indicators of SI is good. It's just the number of times feature I is true. But the second term is a function of the whole parameter set. Not just wi, it's a function of all w. In fact, it's an expectation operation, which means that it's a function of my joint distribution, which means I'll have to do inference. Okay. What I'm trying to say is that you need inference to get a gradient. Once you get the gradient, you know how to update the weights, right? So, okay. So there is this trick. So instead of doing this, because this is very expensive, instead of doing that, people said, okay, let's just change the objective. Okay. Instead of maximizing likelihood for my undirected graphical model, I'm just gonna change the objective. I'm gonna define something called pseudo likelihood and just try to maximize that. Okay, and this is completely, is quite a bit of a change, because once I define my objective to be this, I'm only going to be looking at the parameters of this objective, and these parameters or these factors or these terms need not even appear in my undirected probabilistic graphical model, right? So, yeah, they just change the objective, and with this changed objective, you can do something easier, and that's the point of pseudo likelihood. Because they changed the objective, we need to figure out how to map it back to the original problem. So that's this twist, but let's not go into the detail. Okay. And one final thing, which is not that big of a change, is when you have undirected graphs and you are in the discriminative setting. Discriminative setting is just the same as before, except you'll have a condition on some bunch of random variables. So it's basically the same as before, except some parts of the joint distribution are fixed. Okay, so I just added from, let's say, 2 slides ago, I just added x. Sorry. I just added x. Okay. And if you add x's, this is just the discriminative version. is the same gradient as before, same inference problem that you see on the blue box. Okay. It's because of this fixing of a bunch of random variables, inference may be relatively easier, but it's the same class of complexity. Okay. And there's a final version when you don't know full data. Then what happens is you have to change the first term. You know the first term is no more a function of just the data, right? In the previous two cases, the first term was just a function of data in the gradient definition. Now the first term is a function of my model as well. So you have to do something like EM, okay, where you have to first in the E step, create some artificial data essentially, and in the M step, use the artificial data to compute W's. Okay. So anyway, all these variants exist. It just depends on the problem or what you have. Okay. And most of some of these are necessarily heuristics, or there are a lot of design choices to be made, and we just have to pick and choose what we're going to do. Any questions? So the directed probabilistic graphical model should be easier to understand because it's just count and normalize for every factor that you have. The undirected ones, we have to maximize an objective which doesn't decompose, and that's why we are saying let's use gradient descent, and that's why we were computing gradient. And to compute gradient, I just said let's just use this trick, so it's kind of easy to understand what the gradient is with respect to. The parameters are just Wi's. So that was what we discussed so far. Okay. So in the remaining some 18 minutes, let's look at some applications. So these are hopefully going to be lighter. Okay, what are the applications? So we can sample the following applications. So we are really going to sample. We're not going to go. I mean, we can go through all of them if we had more time, but we have hidden Markov models which are used for time series prediction, time series regression, tracking of objects in videos, tracking of cars if you have sensors, lidar sensors, autonomous driving, whatever. Gaussian mixture models, you've already seen clustering, k-means, so continuous version of that is Gaussian mixture models. Latent initial allocation is about topic modeling, which is an interesting topic in NLP. I don't know, have you guys looked at topic modeling in the previous class? Okay, so you're familiar with this. You might have seen some simpler topic models, maybe we can get to that. Conditional random fields are again, they can be used for classification regression, but they are better tools to use than your regular SVM. Okay, in a sense, they are a strict superset of SVMs, for example.
Can you explain more about how HMMs are used?
We are gonna go into so you care about HMMs or do you care about the other ones? Okay, let's look at HMMs and see. Okay, what is a HMM? It's just a directed probabilistic graphical model which has hidden states and observed states. Okay, so HMM, just think of it as I'm observing a sequence of, let's say, numbers. E1 is observed, E2 is observed, E3 is observed, E4 is observed. Okay. Let's say, in fact, in the object tracking application, let's say it's a sensor reading at time step I. So every second I'm reading where the object is in terms of, let's say, one dimension. Okay. And HI is the actual location of the object at time step I. Okay. In the sense, sensor reading can be noisy, right? Let's say sensor reading can be I add some Gaussian noise and tell you the number, that the location of the object is, at 1 unit. Next, it is 1 meters away or 2 meters away. Okay, so in HMMs, what you define is you have to define again the directed probabilistic graphical model. So you have to define your conditional densities, conditional distributions, right? So you start with H1. So you just define probability of H1. Let's say you don't know where the object is, so you just choose it to be a uniform distribution. Now you define just the transition distributions. Okay, probability of Hi given Hi minus 1. Okay, it's Markov because given H2, H3 is independent of H1. Conditional independence property, and that's why the name Markov there. Okay, so you just have to define the transition probability of given H2. What is the probability of H3 equal to something, and then given H3, what is the probability of emission? Okay. These two conditional distributions and this distribution completely specify the joint distribution of this probabilistic graphical model, right? And I'm also using parameter shading, so I'm not writing a distribution per time step. I'm not indexing it, so I'm assuming that the same distribution, joint distribution, holds across time steps, across any two time steps. I mean, so the joint distribution, okay, of, let's say, what hidden variables take some values, the observed variables take some values, is just this, right? It's just a product form that we've already seen, right? This is the same as what we have been studying in the first lecture. And we can do a couple of operations. We can ask what is the probability that the actual object location is something given the evidence. You know, given E1 is something, E2 is something, E3 is something, tell me where the object actually is. And that's the filtering operation. And the smoothing operation is given everything, tell me where H3 is. That's the smoothing operation. These are just, you can just infer them. If you had these parameters of these distributions, you can infer these. Okay. And I mean, I already mentioned this because there's a single transition probability matrix and a single emission matrix, emission conditional distribution. Okay, these are conditional distributions. So you don't really you have very little number of parameters, but you have a huge number of random variables. Okay, and you can figure these out by just using EM, actually, a variation of EM which is called forward backward algorithm, but it doesn't matter. So you remember the EM, right? We don't observe H, we only observe E. So we can do we can figure out some values of H, update my parameters, and given the parameters, figure out new values of H and so on. Okay. So that is it. This is the model that you can use for time series or object tracking in this case. Okay. Let's look at another simpler model, very simple model, which is the Gaussian mixture model. That's because we have already seen, you guys have already seen the k-means method, right? So the Gaussian mixture model is, I mean, this is just a definition of a multivariate Gaussian. Suppose we have k Gaussians given by their mean and their covariance matrix. Okay, and let's say, and we have these k Gaussians. The Gaussian mixture model description or the joint distribution is just given by sample y from some theta. Theta is just a distribution which specifies like a multinomial, right? So basically, p of y times probability of x given y. Okay, and the mixture model is okay. It's probability of, okay, I should have written incorrectly. I mean, this you can make out. So this is just a normal distribution. Okay, given I pick one of the mixture component. Okay, which is the first line is sample y from theta is just saying what is the probability of y equal to some small y, and given that small y, what is the probability of my xi, and xi is going to be okay. In fact, I don't even have to index xi. Sorry. So the joint distribution is just this. P of y comma x. You have this random variable, you have this random variable. Okay, but it's defined based on k normal distributions, right? And each normal distribution can be picked with probability yi. Probability p is equal to yi. That's all. That's a mixture model, generative description of the same thing. I pick one of the k distributions and then just get a number from there, right? Why a mixture model? Because standard distributions are too limited, and so you want to represent more complex distributions. And so one answer is to use mixture of standard distributions, and standard distributions can be the Gaussian or something else. And it's also a clustering method. Okay. So what does it look like? You have two distributions, let's say the red and this blue one. Then the mixture model can have a joint distribution which looks like that. Okay. For example, you can sample whether red or blue with some probability, let's say 1/2, 1/2, and then you can sample from the red one with which is going to be Gaussian, or you can sample from the blue one which is going to be Gaussian. That's the generative model. Okay. And so the marginal, if you don't know what the red and blue is, the marginal distribution of x looks like this for 1 dimensions. Okay, and in 2 dimensions is the same thing. You have two distributions, two Gaussian centers, and joint distribution. The marginal distribution is just going to be some rescaled version of that. Okay, it's going to be like 2 peaks if you look at the top view. And so how do you learn a GMM? We are not going to go into the detail. It's basically it's the same algorithm that we saw, which is EM with missing information wise, right? In fact, when we defined EM, we were motivating it from k-means, and GMMs are essentially continuous versions of k-means algorithm. So you just follow the EM algorithm. You don't know whys, you just have x as the data points. Given the x's, you want to figure out a mixture model parameter such that it fits the data really well. Okay. So if you pick the number of mixture components to be k, just like in k-means, fix the k, you have the data, all these points. Now you just figure out the parameters of your joint distribution, which is, in this case, let's say there are k, then k-1 numbers for this guy, and for this guy there's going to be mean and a covariance, right? For this guy. Okay. I have explicitly written it here, but let's not go into the detail. Let's get to the third model, which is a topic model, which may be of use to you in your projects. So this is the last thing we'll cover today. Okay. So what are topic models? Topic models are tools for exploring large data sets, which are essentially text data sets. So you have documents, and you want to break those documents into topics. Okay. Topics can be, for example, politics, religion, sports, and so on. And so one of the applications is you have a new document, which is basically a sequence of words, and then you can ask, what is this document about? That's the inference problem. So you have evidence, and you can ask what the inference is. Okay. And latent Dirichlet allocation is one of the simplest and widely used topic models. One of the widely used topic models. Okay, so what does the model look like? Okay, so the model has 3 parts. So let's focus on the first one. You sample the document's topic distribution, theta. Okay, so theta is sampled from a Dirichlet distribution, and that's why it's called Dirichlet allocation, the Dirichlet part. Latent because some random variables are not observed, so that's why it's called latent. Okay, so latent Dirichlet allocation is just a graphical model in this case. So we're going to draw a distribution over topics, which is the theta. Okay, so think of that as a multinomial distribution. Okay, so you have politics, religion, and sports. Politics, religion, and sports. So maybe you have 0.5 probability of this, 0.2 probability of this, and then remaining 0.3 probability of this. This is going to be the theta. You sample one of that and just keep it. Okay. I'm just describing the generative process. And then for each word, okay, in your document, let's say your document has n words, okay, you sample the topic zi of the ith word. You have n words in your document. Let's ignore what the words are. Let's say you want to have n words in your document. Okay. For the first word, I'm going to pick a topic, draw a random variable from theta, and that's going to be the topic for that word. And I'm going to do that for all the n words that I want to have in my document. Okay. And then once I know the topic for every word, I can just draw a word from each topic. Let's say the topic is sports, then it will have sports related words. The topic is encoded as again a multinomial over these words. Okay, so let's say it's sports, then sports is the topic. Then word like win or player. There will be many words, and it's a multinomial. Actually, categorical distribution, but anyway, it's just a PMF. If it's confusing, it's just a PMF. Okay. So for every word, I know what topic it should be. If it's sports, I'm going to draw one word from here, and that's how I'm going to populate my document. That's the generative process of how to create the document. Okay. And when I do this, you can think of document being a collection of words, collection of topics where where these words, some words are selected, right? Is the process clear of how I'm creating a document from starting from scratch? I'm sampling a theta, which is a distribution over topics, right? I'm keeping my theta. From theta, I'm going. If I want to have a document of n words, from theta I'm going to draw n random variables. Okay. Each random variable will tell me whether that word should be a politics related word or a religion related word or a sports related word. Okay. And then let's say the word is supposed to be a sports related word. Let's say the ith word. Then I'm going to draw from PMF, which will be a distribution over the words, right? I can just, if it's sports related, then there will be high weights on the sports related words and maybe 0 weights on politics related words. Then if I draw a word from there, it will be a sports word basically. That's all. That's the generative process for LDA. Or if you want to look at the notation, it's the same as what I just said. For a document, just create a theta, and then for every word in the document, you create which topic it should be. And once I know the topic, I'll just sample a word from that appropriate topic distribution. Okay. So this is actually a graphical model. You can expand out this is called a plate notation, and you can expand out. It's going to be just a graphical model. Okay, directly graphical model. You can contrast that. So this is actually LDA is actually an admixture model. So there is a simpler topic model which you can also think about, which is as follows. Okay. You again have a distribution of topics. You pick a topic, and then you sample all words from the same topic. Okay. This is called the multinomial naive Bayes model. Okay. The document is generated from a single topic, and here the document, every word is generated from a potentially different topic. That's all. Given these generative models, you can actually figure out all the stuff that we have been talking about, infer the marginal probability of the hidden variables, the conditional probability of the hidden variables, the parameters of this topic model, and so on. All the methodology that we were talking about applies to this. Okay. So those are the three models that we have looked at: HMMs, Gaussian mixture models, and LDA. We were going to skip conditional random fields, okay, which are just there's nothing interesting going on there. So let's summarize. So we discussed the family of approximation methods, which are called Markov Chain Monte Carlo methods. We looked at Gibbs sampling, and we looked at Metropolis-Hastings sampling method. Okay, Gibbs sampling, we went to a little bit more detail. Metropolis-Hastings, we just defined, okay, sample in this two-step procedure where you get a sample, it's a candidate, you accept or reject with some probability, right? That's okay. They are Markov Chain Monte Carlo methods, very useful tools. Next, we looked at parameter and structure estimation for these graphical models. For Bayesian networks, at least the parameter estimation was easy, okay? But structure estimation was complicated, and in fact, for undirected graphical models, the parameter estimation involved inference. Okay, and we've also looked at some applications, which at least the keywords you should remember: GMMs or HMMs or LDA or CRF. They're all special cases of the graphical model machinery that we have looked at in the past 3 lectures. So when there is structure in the inputs or outputs of a machine learning pipeline, you should go with these types of models, directed probabilistic graphical models or undirected, compared to vanilla methods like logistic regression or SVM or something like that. Okay, so that's it for today's class.